Off you go.
See my screen?
Not yet. Okay, now I started.
Okay. So we just started. I somewhat doubled. What the fuck?
Don't swear, don't swear.
That's fine. Okay. So we started with some exploration for the data, as always.
Okay.
And
Okay.
we got into the data set. Looked at the data, normal stuff. We looked at some distributions. So first we saw some null values in the data and looked for what transported really is in the data. So it's nearly the same. So half of the data, half of the passengers will be transported, the other half not. Then we also looked at some distribution of the age of the other values, like food court, shopping mall, spa, the luxury stuff, the RDEC, and also we start with some preparation of the data set. But since two people worked on the data set, we had some different approaches. So I will prefer going with the TensorFlow decision forest. And my other teammate, which is Carl Works, he worked with the AK-Learn model, and I will also present this here now too. So what he does, he dives a bit deeper into the decision forest, decision tree. We haven't done anything on random forest yet, but for decision forest, for decision tree, what the fuck? We got some exploration in metadata too. Sorry?
Always swearing. Don't swear, don't swear. What if this was a job interview and you start swearing in the middle of a job interview, you know?
Luckily, it's not.
Luckily, it's not. Yeah.
So we did some transformation of the data here. So put the data into integers and split up passenger ID into group number and number for better working in the later work. And also what we can see here now, that all the null values actually now has a value. So it's better for working on it. Also, the home planet is now not anymore a name, it's a number now, which also makes it easier for later exploration. And now we dive into the decision tree. So we split it up in a training and test data. And Y obviously is the 13th value, which is the transported value. So we can now train the classifier on it. And what we can see at last is our first decision tree. It's like the first version of it, but as you can already see, we have the decision tree here, which is split it up by destination at first sight, and then on room service and cabin. And at the last step, you can see there's already a place where our decision tree is pretty sure, I would say, on this classified true. There we have like 100 samples. On the other side, we have 12 samples on false. The other value here on shopping mall, we have also a pretty high value on true, but the others aren't that sure. And maybe just one quick step here. What we have done here is, with the Gini criterion, but we had picked the max depth of 3 and a minimal sample leaf of 5. So we can probably test around with that too, but for now we only have gotten into this. Actually, for interpretation reason, we have maybe do some other work on the home planet, since we switch some values into integers. We can now not really interpret which of these values are anymore, or destination even same. So when destination is split up at 0.5, we don't know which destination it actually is, since we did them into these values. But for now, that's what we worked on, and we will probably dive deeper into random forest and also on this decision tree.
Okay, very good, very good. So the group is 5 people, right?
It's 5 people, yeah.
Okay, and everybody's everybody's working. Very good.
Everybody's working and doing great trips.
I mean, when they're not, when they
everybody's
don't
happy,
go, when they don't go to Kenting for a long weekend, right? That starts on Wednesday. But
Yeah.
anyway.
Yeah.
Okay, very good, very good.
Okay.
Next, who wants to go next, guys?
I can present challenge 3, but I only do
Okay.
half. Here is challenge 3. Here I import the NumPy some tools we need to use, and already face data. And first we start the SVD. SVD. So this is the SVD reconstruct. From this we can find US and VT. So next I show the U. This is eigenface. From the graph we can see the K increase, the UK. The graph of UK did not impact a little only. So
Wait a second. So all the rows are the same, right? I mean, the
this
first
is
row,
UK. What?
I mean, but you only have 2 rows, right? The rows 3, 4 are the same. Rows 2, 3, and 4 are the same, right?
2, 3, and 4. This?
No, the rows in the picture.
Yeah, this is UK and the UK. This is not.
But they're all the same, right? They're all the same. Look at it.
It look very same.
It's the same. It's the same. It's the same. It mean you did something wrong in the code. You just pasted you just plot the first row multiple times. Check a second.
Is UK is, but the virtualized AK is.
Then it changes. Yeah, then it changes. But go up a second. Let's fix the code. Go up. There. No. Stay here. SVD reconstruct AK. Then for I in range, I am sure. Why is it always the same? Fk is equal to k. Set title Fk is equal to k. For k is there. What is the error? Index k. Yeah, there is something to fix here, eh? Because SVD reconstruct AK. So the k is there. U. Guys, where is the mistake? Try to run it. There is something wrong. Yeah?
This is UK, not AK.
No, but there, the UK is calculated in line 10 there, right? You can see in line 10, you calculate the U.
Yeah.
Then, the A is the original one? Where is the A coming from? Yeah, it's the same.
AK here.
Okay. Go up a second. So the AK is missing there. There you just use one A. Okay, doesn't matter. But yeah, just fix it. There's something wrong. Yeah, there's something wrong for sure.
This is the AK result.
Okay, this makes sense. This makes sense. This makes sense. This makes sense.
Then we print the reconstruction error. I use this function.
Yeah.
Then we can find the K increase the error is reduced. Next is NMF. So this is the NFS construction. Next, this I print the W. This is the result of W.
Stay there a second. There is something. Did you invert? Why are the colors inverted? Yeah, this. Why are the colors inverted? Why are the colors inverted? You see that some of the pictures have the colors inverted, right? Yeah. Okay. Weird.
Then this is the result AK.
Okay. This makes sense. Yeah, this makes sense. Okay.
Then we also print the error. Now that's we compare the SVT and NF. This is original SVT and this is NFF.
This one here, there is no difference. Yeah, let's see the next one. This
is K. This is K equal
25. Difference is minimal. Yeah, difference is minimal.
This 50.
Yeah, it's like pixels. There is the difference between them is just difference in pixels. Yeah. You can see the upper lip is a little bit different in the two reconstructions. That's it. Otherwise, they are identical. Okay, very good.
Yeah. Finish. I complete it before we end.
Very good. Yeah. So for next challenge, right? Try to find someone else. Yeah. It should be 3 of you, right? If you look at the student Ang something Ang. Okay. Very good. Let me take my notes. Anything else? Anybody else that wants to present?
Yeah, I'm presenting on behalf of Wan Shitong.
Okay.
Yeah. Let me share my window.
Yeah. Present challenge 3. 3. Wan Shitong. Okay.
Challenge 4.
So they didn't invite you to go to Kenting?
No. I think today is the sports day. That's why not much people come. Yeah.
Of course. So I think the people took a long break, right? So
yeah,
if you skip today, then you come back on Sunday. Yeah, it's okay. It's okay.
Okay. So
you don't like sports? That's what you're saying, that you don't like sports.
I'm not involved.
Very good. Go ahead.
Okay. So basically for this data set, I think there's quite a lot of missing values and we have to do quite a bit of data cleaning. So for example, for the passenger ID, we can see that it's made up of group and the passenger number. So we can make use of this group number to fill in some of the missing values, such as from the home planet, because people in the same group should come from the same home planet and should have the same destination. So basically, that's what we did. We tried to fill in the home planet and so on based on the groups. And also for the Cairo sleep, right? Since passengers are put into suspended animation, we think that there shouldn't be any money spent on the amenities. So if they add up to be zero, they should be true. Yeah. Otherwise, they will be set to false. Yeah, this part. Yeah, then after that, we try to fill in the rest of the numeric columns with median or mean, and then we try to convert it to Boolean as well. Then one hot encoding. And then afterwards, we did the usual decision tree and random forest, but I didn't print out the decision tree now. But here's the results. And then we submitted it on Kaggle to see the scores, and here are the scores. Yeah.
How was your score? How did you rank?
It's, can you see the score? Can you see my screen?
Well, no, well, we still see the localhost webpage, yeah.
Oh, no wonder.
You have to change the sharing to the screen.
Okay. Okay. Yeah. So here's my score. For the random forest is 0.78, and for the decision tree 0.73. So random forest did better. Yeah. Then I think moving forward, maybe we can try to improve our score.
Yeah, of course. Because there is a lot of data engineering that you can do. So I'm not concerned. I'm sure you can come up with something nice. So the group, 5 people, right? 5 people. 5 people. Yep. Okay. 5 people. And any comments from last week?
No, presented last week.
Okay, good. Okay, very good. Anything else? I think we're good for today, right? We have 3 groups. So let me do a little bit of presentation on something, and then we move on. Then I don't want to stay here too much because so today is sports day, right? So as you said, I don't want to penalize the students that don't attend class, but it's okay. Okay, let me share. Am I already sharing the screen? Oh, am I already sharing the screen? Let me share the screen. If I click present, if I click present here, it starts right away. If I do here, the presentation starts, right? You guys can see the screen, correct? Guys?
No, I don't see anything.
Oh no. Okay, so I have to do. Let me do this. I thought that when you share, I thought that when you present in, in Chrome, it understands that you're trying to present on the Google Meet as well. Okay, I'll start here. So we'll do some bagging. So for the final project, then I think, because we were discussing before, I think we're just going to start. We're just going to give it away next week, and then and that's it. We do the music thing, and then you'll have until the 20th. 20th is the presentation, and then a couple of weeks after, we'll let you submit the final repository and the presentation and so on. Should be okay. Okay, share. Where is the? Why is it? Just a second, guys. I don't know why. Where's the issue? Where's the issue? I cannot share my. Where is my? Okay, here we go. No, it disappeared. Share. Okay, we should be good. Okay, so let's discuss. So you can see everything, right? Bagging.
Yes.
So little joke, right? Little joke. It says, "Oh, if a binary tree wore pants, how would you wear the pants?" Okay, very good joke. So let's do a quick review of decision trees. Then we discuss bagging. Then we discuss out of bag errors, and then we do variable importance. So let's start with the review of the decision trees, right? So this is what we saw in the last couple of weeks, right? That sometimes it is easy to separate data if there is a linear boundary, but if there is a more complex boundary, then it would be very hard for us to create a model that separates the data in, let's say, non-complex regions. So in order to tackle these cases, right, we figured out that we can use decision trees where basically it's an inference, it's a regression or classification or structure in which you choose a variable, you create a split over that variable a certain step, and then you proceed inside the region by splitting using another variable. Okay, so if you do this, then you come to these beautiful decision trees, and yeah, and that's what we discussed. So in general, creating the optimal decision tree is too hard. So what we do usually just to use a greedy approach. So we start with a node containing all the data, and we keep splitting the data in the subtree based on a certain variable until a certain stopping condition is met. And so we discuss the stopping condition, either the entropy or the Gini index or the variance. And then we repeat this until we get to a leaf. And once we get to a leaf, we're going to produce a prediction. This prediction could be a regression type of prediction. So it could be a value for the class, or it could be a classification. So it could be a category for the elements in the class. So the stopping criteria, we said that the stopping criteria are very important because we want to maintain a certain balance in the tree, a certain depth in the tree. We don't want the model to grow infinitely complex. So the idea is that for classification, we use the purity of the region. Okay, so we see how many elements from another class are contained in the current leaf, in the current node, and we decided whether to split based on this criteria, or we discuss how we can also use the entropy or the Gini index. And for regression, it's clear that we can use, for example, the MSE of a certain node to decide whether to split or not, and we will decide to split only if only if there is a sufficient increase in the MSE of the subregions. So for classification, we label each point region in the model with the label of the class that has the majority in the region. And for regression, we can choose the average of the values of the elements in the certain region. Good. So the stopping criteria is usually maximum depth or a minimum MSE. And there are other common stopping criteria. There is if the class contains labels of all the same class, don't split. If the number of businesses is below a certain amount of minimum samples, don't split it. And if the total leaves of the tree are too many, don't split it. And only split it if you gain enough purity to do so. Okay. This plot again is expressing, as we saw last time, the idea of overfitting this decision tree. As always, we have a bias and variance trade-off, right? So with only one class, we do very poorly. With two classes, we do better. With four classes, we do almost perfectly. Then if we increase the depth from 4 to 20, there is only marginal improvement. And then we can go all the way to 100, and we see that we have overfit the data, right? So that's a usual discussion on variance and bias. So if you look at the tree complexity, during training the tree depth. As you increase the tree depth, the loss is always decreasing. But then if you check the loss on the validation, then there is a clear minimum in the loss for the validation data. And if the tree is shallow, then you have a high bias and low variance. And if the tree is too deep, then you have low bias and high variance. And this is the classical trade-off that we have. So if we are in a shallow tree, then we can improve our stopping criteria and let the tree grow bigger. And if we are in a deep tree, what we can do is that we can implement pruning, right? So that's what we discussed last time. And yeah, classical picture here, where we have different depths, different amount of trees, and use train validation or cross validation to estimate the best depth of the tree. So if you're happy to grow your tree multiple times, you can do a model selection based on cross validation. Very good. So the nice thing is that decision trees are highly interpretable and they run very fast because doing inference, you're just doing comparisons on a single variable. So the computational complexity is very low. But they let you capture very complex decision regions, right? Yeah, the boundary of the decision regions can be very complex. Of course, they are prone to overfitting, and so in practice, decision tree actually often outperform other classification and regression methods. Okay, so if you compare, for example, with a classification DNA, of course, the classification DNA is going to be too better. Okay, so we have a model that we like. It's interpretable. But it has this type of issues. So what can we do in order to reduce the issues? Okay, so let's start from the same plot as before, 2 regions, 5 regions, and 100 regions. Then we can do bootstrapping, right? So to check the performance of the model, you can always do bootstrapping. So now we see here that we had this model, right, over a certain train test split. Then we redo the train test split, and we see that, of course, the model for depth 2 is a little changed by the change in the data set, and the depth 100 is very much changed by this. And so what we do is that we can try to combine the prediction for the different models that we obtain through bootstrapping. Okay, so now you see here that we have a shaded region for each of the 2 models. And of course, when the shaded regions, they superpose each other, then you have a darker shade. So you see here that for the shallow tree, you have very much superposition between the regions, so there is a lot of darkness. Depth 100, there is very little superposition between the decision regions, and depth 5, we have something reasonable. Okay, now you see already what's going to happen, right? So the trick that we're going to use is to repeat this process multiple times, and we're going to see that the models gain a certain consistency, okay? So here again, these models are very much consistent. Here the consistency will be lower, but seems reasonable. And here there is very little consistency. Okay, good. So now we are happy to pay a certain, okay, we can keep doing this more and more. And as we move across different iterations, you see that you have very good regions of consistency in the predictions. Okay, so we can do this, of course. There is no particular problem because the trees are very efficient. So we could train 100 trees with the time that it takes us to train a DNN. And we use bootstrapping, right? So we have a whole data set. We do different validation versus test split, and then we train the data. And then the idea is that we aggregate the output of all the trees. And we use this for producing a prediction. And this is called bagging, which is the short for bootstrap and aggregation. So bagging. For classification, we return the class that is the most popular in a certain, for the polarity of the model. And for the regression, we again return the average of the outputs of all the trees. So we took a simple model that was underperforming. We figured out that we could create an ensemble method out of this, right? So we could combine the decision of different methods in order to increase the performance of this model. And what did we gain? Well, we still have a fairly high expressiveness. So because if we use deeper trees, then we can approximate complex functions. And intuitively you see here that this region is roughly a round region, right? And it would be hard for us to find a deep enough tree that captured the round shape of this data set without overfitting. But now if we look at this region as a combination of many shallow models, then the emergence of the circular boundary, it's clear, right? It doesn't lead to overfitting. So you can have a more complex boundary that doesn't result in from overfitting. And in general, there is a low variance because the more trees you're happy to use, then the average prediction of the models will improve the final prediction. And of course, you pay a price in complexity, but everything is a trade-off in life. Okay. So now we look at the regression problem, right? So you see here that we have the data set with the light and dark red points. Then we have all the trees in the ensemble that are the blue ones. So you see that the boundaries are very sharp because the prediction, it's a shallow tree, right? So the prediction, they jump very much from one leaf to the next leaf. But then, of course, if you smooth out things, right? If you take an average of all of this, then the bagged model, it's smoother and produces a better prediction. So then, if you look at classification, then we are a little bit in trouble, right? Because we said that when we had a single model, then we were happy because we had it was very interpretable, right? Now our interpretation is not as clear as before, and now it takes on a statistical aspect, right? So here you see that it's again the heart rate, right? So you see that we have the split of these variables, and we have the ensemble of the models, and so you can see that across these models, right, you don't get a split over a single variable that you can interpret as in some way, but what you get, you have a certain distribution of the features, right? You can see of all the models, right, that they take a decision for the glucose. I can plot the number of models which give a certain relevance to the glucose for the final prediction. Okay, so you see here along the tree, right? You get the different distribution of the different trees, and eventually, when you take a decision, you can see the plurality of the votes, right? You can see for each node how many trees agreed to give this as a no hard condition, this is a yes hard condition, and vice versa. Okay, so you see that now the decision is not the interpretation of the tree is not as simple as before. You retain an interpretation of this, but of course now you're dealing with distributions and things are generally more complex to convey. Okay, So do you see any problem? If the trees are too shallow, then we can still overfit. Some of the trees can still overfit if they are too large, and the interpretability is the major drawback. Okay, because this and other ensemble methods, which is the more general class of methods that this particular technique belongs to, is that the average models is no longer easily interpretable, as you cannot trace the logic of each of the single trees, but you can just obtain a statistical description of the way in which the average tree behave. Okay, so let's do the case of underfitting, which we saw was an issue here. So again, we take a depth 3, 5, and 8. Clearly here 8 is the correct model, okay, because you have these two distinct clusters, and if you have smaller depths, then you cannot achieve this. So if you again do bagging, then you see here that this region is low variance, but this region is high variance. Okay, so even if this region is the correct, let's say, is the correct depth conceptually, because you recognize the two clusters, you see that you don't get there. So if the tree is too shallow, then you can underfit. So you see here that you don't get the clear separation between these two clusters. And so how do we decide what is the correct complexity of the model? Of course, the depth of the tree is a hyperparameter. when we want to settle something about the hyperparameter, then we have to pay a price, and the price that we pay is cross-validation. Okay, we have to repeat the fitting experiment multiple times, so that what you do is that you obtain a distribution of the performance as a function of the different tree depth. You will see what is the variance of the performance at the different tree depths, and then you choose the tree depth that provides the best performance when averaged across the different cross-validation slices. Okay, good. Let's do another set of slides, and then we let it go. So this is bagging. Let's do another set of slides. We said, just a second. We just discussed bagging. Let me find. I prepared the slides and then, of course, I messed up. Okay, bagging part 2. Okay, let's do bagging part 2. Just a second, guys. Just a second. Okay. And then it's not, my computer is fairly slow today. Don't ask me why. Okay, back in part 2. And then we go into presentation mode. View full screen. Okay, and we're good. And we're good. Yeah, you guys can see this, right? Okay, good. Very good. So let's continue on the bagging discussion. So we said we were here, right? We said bagging is bootstrap and aggregation. We gave this nice example of the average case, so we can combat overfitting. And this is classification, and then that major drawback is the loss of interpretability. And here there are cases of underfitting and a case of overfitting. Okay, even when we do bagging. Of course, as we said, you can do cross-validation to try to recover something. Okay, now let's look at the out-of-bag errors. Okay, good. So remember that we start from original data, then we do bootstrapping, right? So we have a certain subset of samples that we use for training, and then we see the performance of the decision tree over unseen and unused data. Okay. Then we repeat this object, we repeat this operation again. We select a different subset of samples. We have another decision tree, and then we have other performance over unused and unseen data. Okay. Then you put this all together, and what you do is that you take the average of these three models, and then we said for classification, you take a majority vote for the certain label. So you go down over each tree, and you see what is the label given by each tree over this specific input, and then you give the output as the average of the votes. And for regression, you just give the mean. Here there is a 1 over missing, but doesn't matter. And then in the first case, the error will again be the misclassification error, or the misclassification error. And then here you will have the MSE loss. Okay. So then you look at the error that you produce. As we said, here you divide over the number of trees in the bag for the error for each label. And here you have again 1 over the batch, some of the misclassification error, and for the MSE 1 over the batch, the error over the single elements in the batch, and then you average over the batch size. Okay. So as we said, we refer to this model as an ensemble method, which is a way of building a single model by training and aggregating the output of many models. So when you look at ensemble methods, you cannot look at simply the average error across the ensemble. You will be missing some aspects of the combination of the different models. What you have to define, what people find useful to define, is the out-of-bag error. What is the out-of-bag error? So given a training set, an ensemble model, each trained on a bootstrap sample, we compute the out-of-bag error as the average model by. For each point in the training set, we average the predicted output for this point over the models whose bootstrap set excludes this point. Okay, so for this, we're going to see a plot later, right? But when we take the models that haven't seen a certain sample, and we look at the error that we do over this sample over the models that have not seen the sample, we compute the error or the squared error of this average prediction, and we call this the pointwise out-of-bag error. Then we average the pointwise out-of-bag error to get the bag error when we average over the full training set. Okay. Variable importance. Okay, so let's calculate the total amount of MSE regression or Gini index for classification, how it's decreased due to splits over a given predictor, average over all the trees. So when you build different trees over different sets, you have no guarantees that the split variables will be the same over the different subtrees. Okay, so you can split over age first, you can split over sex first, depending on the different test and validation that you have chosen. So it is tricky then to recover an idea of how important is a certain variable for the prediction. Okay, so you would like to come to this type of conclusion where you get a variable importance, meaning that you look at each variable over the 100 trees with a certain max depth, and you see what is the importance given by bagging to a certain variable. So how do we improve over bagging? So in practice, the ensemble of the trees in bagging tends to be highly correlated. So what we do with bagging is that we tend to produce very similar predictions because the splits tend to be very correlated. So let's say that we have a strong predictor as J in the training sector, and then many other model predictors. Then the greedy algorithm that picks the variables to split first will always start from the same predictor, and so that then all the trees they're going to start with the same predictor, so that they will end up, let's say, with similar predictors. So there's going to be a correlation between the predictors, because after the first split, let's say the data set, the data is split equally among the 100 trees, right? So even if you have 100 trees, they all are similar because they all start by splitting the same variable. But for us, right, when we take the mean or the average of the prediction, in the back of our mind, we have assumed that the ensemble is independent and identically distributed. So we can take the prediction of each tree and equally evaluate the contribution of each tree because they all act independently. But this is actually not the case, right? We're making a conceptual mistake there. So how can we see this? Okay, let's say that you have a B identically distributed variable X, which is variant X squared. Then what you see is that if you combine all these random variables, then you observe a decrease in the variance of the mean of this random variable as sigma squared over B. Okay, so let's say that you have X that is normal 0, 1. You throw 100 uncorrelated X's, then you sum all them up together, and then the value that you obtain will be a value around the value 0, because they all have a 0, and the law of large numbers is kicking in. And then you can ask yourself, if I repeat the same experiment 100 times, or 1,000 times, or 1,000,000 times, how is the variance decreasing of my estimate of the mean of the distribution? Will be always sigma squared over B. Okay, so there is a linear decrease of the variance of the estimate of the mean with the number of samples. So if you go ahead with this logic, then you could say, well, what now if I add some correlation between the variables, right? Then how is the correlation between the variable decreasing the convergence of the mean estimate to 0? And the answer is here, right? In the case where you have a correlation rho among the Gaussian variables, then the decrease is sigma squared times 1 plus rho squared divided by B. So this 1 plus rho squared, right, is basically destroying, it's destroying the correlation, is destroying the convergence to the mean value of distribution. Okay, so IID variables, they contribute all new information, let's say, regarding the mean of the distribution. With the correlated data, they contribute, they contribute less information with respect to the true mean of the distribution. Very good. So we are a little bit in trouble because we haven't decided how we're going to deal with this. Okay. Why the slides froze? Okay, we have to switch. We have to switch to the part D of the distribution. Let me change my slide set. Back in part B, back in part C. So this brings us to the next topic, which is random forests. And we're going to do it now. My computer is super slow, guys. Bear with me. View full screen. Of course, the solution to the problem that we're discussing now is to enforce independence between the three. And if we do this, then we obtain what we call a random forest. Come on, switch. Okay, good. So this is a modified form of bagging that creates an ensemble of independent decision trees. And how do we correlate the tree? For each tree, again, as before in bagging, we'll get a separate bootstrap sample for the full training set. Nothing changes. But then for each tree, at each level, at each leaf, at each node, we will randomly select the predictors from the full set of predictors. Okay, so at each node, you will select a subset of the full predictors that you can split over. Let's say if you are splitting over a single variable, then this variable will be randomly selected at each node. Okay, this is how we enforce the. This is how we enforce the. This is how we enforce the trees to be independent. Okay, so what are the hyperparameters of this improved form of bagging? So the number of predictors to randomly select for each split will be a random variable. So let's say that you go from 1 to the full set of predictors. If you allow for the full set of predictors, then you are back to bagging. If you have only one set of predictors, one predictor, then everything becomes random. But you can allow, for example, to choose between 5 randomly selected predictors at each step. So you can still do the greedy algorithm, because the greedy algorithm is still selecting under this subset of parameters which is given to you, but you enforce independence in the choice, because different trees will have random selections of which trees to choose over. Okay. Then again, we have the total number of trees in the ensemble and the maximum depth of the tree, or the minimum leaf size, or some other measure of complexity of the tree. So in theory, each tree in the random forest is full, but in practice, this is too expensive. So it's always good to have a minimum node size for this. Okay, now we have a new model which we call the random forest, and of course we want to do some tuning of the parameters. So there are standard values of each random forest hyperparameter recommended by practitioners. Okay, but generally these parameters should be tuned using the out-of-bag errors, as we discussed it before, right? So then, for example, the number of predictors to randomly select at each split should be the square root of the total number of classes for classification, and the total number of samples divided by 3 by regression. Good. So this is again just a practitioner choice, right? So in the for regression, you can be more generous. You can allow the algorithm to choose among a larger set of predictors, but for classification, you want to use a square root, right? So you want to be more aggressive in restricting the number of features that you can select. And of course, for tuning this value, you will still use out-of-bag errors and cross-validation to have a to have a hint on the variance of your predictor. So now how we have to define the variable importance for a random forest. So the variable importance can be defined, for example, using the mean decrease of impurity, the MDI. So as in bagging, right, we will get the purity of a certain leaf. Then we will see the purity when we split this node into two leaves, and we can see what is the decrease in impurity of this split. And then we can go throughout all the trees, and we can see all the trees that split the variable, and we can have a mean decrease of impurity for all the times that the variable was split.
Sorry, Stefano.
Yeah, go ahead.
Do you share slides with us? Or?
I thought that. Sorry. Let me share.
I mean,
Sorry, I
I
was talking to myself.
It's hard to follow without this one.
Yeah, no, it's because the computer is it must be updating or something. So it's I clicked, but it didn't happen. Here we go. Here we go. Sorry. Now I cannot see anything. Very good. Here we go. No. Yeah, sorry, my computer issues. So we said this object, right? Then yeah, so this is it. This is the outer bag. There was no picture. Yeah, there was no picture. Thank God. We didn't skip any pictures, so just my poem voice. Another way of selecting the variable importance is using the permutation importance. So you could record the prediction accuracy of the OOB samples for each tree. Then you randomly permute the data on a certain column in the OOB samples, and then you record the accuracy again. Then the decrease in accuracy as a result of the permutation is average over all the tree, and is used to measure the importance of the variable J. Okay. Good. So what you do here is that you keep the same way of distributing the variables in each node in each of the trees in the forest, and then you permute the two variables, let's say, on the samples, and then you see of the decrease of accuracy in this permutation, and then you use this as a measurable variable. And then there is the one step further, which we'll see in the next lectures, no worries. So, but basically after the variable, once you choose the way of measuring the variable importance, then you will get something like this. So basically you want to know what are the predictors that dominate your prediction. So that basically what you do is that you gain back the interpretability of your random forest, okay? And you can compare then the variable importance between random forest and bagging. And you can see that in this case, for example, they're very much aligned, right? They're very much aligned. And this is because, the variable importance should be sort of abstracted away from the specific model that you have. Okay. Some final thoughts on random forest. When the number of predictors is large, but the number of relevant predictors is small, then the random forest can perform poorly. Okay. So because if you have very few predictors that you really need for your decision, then the randomly selecting some irrelevant features for the prediction can only create confusion in your model, right? So because at each time that you do a split, the chances that you select a relevant prediction will be low. So most ensemble in the tree actually very weak models, and if you do an assembling of very weak models, then nothing happens, right? So increasing the number of the trees in the ensemble generally does not increase the risk of overfitting, okay? Again, by decomposing the generalization error in terms of bias and variance, we see that increasing the number of trees produces a model that is at least as robust as a single tree. Very good. However, if the number of trees is too large, then the trees in the ensemble may become more correlated and increase the variance. Okay, very, very clear thoughts. Now, the important part of this is that random forest classifiers or bagging can actually return probabilities. So it is very crucial that once you have a model, that you can have a measure of reliability of the decision of the model. And so you would like to have a model that has a soft output, right? You would like to have a model that outputs a certain probability distribution over your classes or over your regressed value, so that then you can have a certain confidence of the variance of the prediction. Yeah, And this is, yeah, it's clear how you do this, right? Because since you're assembling most of the model, you can just look at the statistics of the ensemble. Where do data scientists go camping? In random forest, very, very random. Okay, good. Then the next, we have a couple of lectures left, and we're just gonna do some, some more ways of dealing with unbalanced data set, categorical data, and missing data. And after that, the class, the frontal class will be over, and you will have a month, I think, 3 weeks for 3 weeks until you can. You'll have a month to work on the final project. After 2 weeks, we will have again a mid-project presentation, and then everything will be over. And unfortunately, the class will be done. Okay, good. Any questions? Any other comments, guys? Okay, then I stop recording.
Yeah, actually, sorry.
Go ahead. Go ahead.
Isn't there a way to bring more interpretability back to this bootstrap aggregation? Like do the bootstrap aggregation and then afterwards do whatever magic to bring back interpretability in a way?
Yeah, I mean, what you can do is that when you do the aggregation, right, you can see all the models. Let's say we look at classification, right? You can see how the models predict for certain elements in the test set, let's say. And so what you can do is that you can gain something about the variable importance, but you can say which variable is more relevant for the decision. But what other type of interpretability would you like to take back? Like maybe some correlation across the variables. What did you have in mind?
I mean, by decision trees, you can really like trace the way back on where the most decisions were made. That's actually with barrier importance, it could be possible a bit, no?
I mean, you will have to see. For example, you could go, instead of looking at the variable importance, you could look at pairs of variables, right? You could see how many times you split over a certain variable at once, and then the next one you split over the other. And then you could try to have a certain notion of the longest splitting chain or the best splitting chain of, let's say, 3 variables, because those 3 variables, 4 variables, they always split one after the other. But it becomes very hard. It becomes very hard. Also because here we're talking about hundreds of models, right? Because the single model is so cheap to implement that. So my answer to you is only partial. Yeah, only partial.
Okay, thanks.
But that's also philosophical, right? That's also, you have to see this as a philosophical issue, meaning that the more complex the model it is, the more it is hard to get an intuition out of the model, right? So it doesn't matter if it's a bagging or if it's a deep neural network, right? So as the number of parameters increases, then the implemented function, which is harder to analyze. So it's a bit philosophical. Okay, so if there is another question, then we see each other next time, guys. And